Hi, I'm Alex Lamb, author of the Roboteer science fiction novels, and you're watching Secrets of the Universe, the exciting video sequence in which I attempt to answer every single question that has ever happened, ever, and fail. Fail, frankly, ladies and gentlemen, but we don't mind because we're going to fail well. So what's today's video? Today's video is about infinity. A strange and magnificent topic. What is infinity? Infinity is how we reason about unlimited scale or unlimited smoothness. Everybody's heard of infinity. It shows up in children's conversations. It's like, well, I win 10 times. Well, I win 11 times. Well, I will win infinity times. Ha! So yes, that's the context in which many of us first encounter infinity, I suppose. But so anyway, that's it. Why is it interesting? Well, because it plays a contributing role in a variety of major scientific theories. Also, it's mystical and strange, which is, I think, a good enough reason for me to try to cover it here. And my favourite reason, because our understanding of infinity is massively broken, in my opinion, ladies and gentlemen, and can be fixed. Welcome to the Infinity Doctor, and I am he. All right, what are we going to... So why is it broken? What do I think is the problem with infinity? Well, here's the thing. With infinity is essentially what springs out of a human reasoning process that happens. Infinity is, if you like, the product of a mental process that is how you might describe as the assumption of symmetry at scale. And what I mean by that is it's very straightforward in the mind when you're trying to reason about things that appear to be smooth to imagine that they are infinitely smooth. Or if you are trying to reason about things that appear to go off like as far as you can possibly see, to presuppose that basically that they go off forever. That just simplifies the work that the human brain has to do. So for many, many years in history, people used to think, for instance, that water. Cheers, by the way. They used to think that my glass of water was infinite. You could take a whole glass of water and you could pour half of it out. And if you were sufficiently careful, you could pour a quarter of it out, or an eighth or a 16th, and carry on going like that. And that there would be no limit to how little water you could have in a cup. Because water was obviously a slippy, slurpy thing and was smooth. And it took an incredible amount of time and effort in science, ladies and gentlemen, for us to finally put to rest the idea that water wasn't perfectly smooth. There were tremendously well-established scientists in the 19th century. Nonsense! This theory of atomism is pure poppycock! They did that forever. And the only thing that really put the finishing on that whole idea of smooth matter was when people were actually able to detect atoms. Einstein's work on the photoelectric effect and things like that finally put an end to the idea of smooth science, because it was the smooth things, because they were so seductive, ladies and gents. Despite the fact that people had some intimations of the fact that this was true since Democritus back in the time of the Greeks, there's always been people saying, no, atoms, rubbish, what's that? And the same thing that happens with distance, that people always used to think, up to and including Einstein, that for instance you could jump back in time, you go back 1 year, 2 years, 4 years, 8 years, and so on and so forth. Clearly, you could always ask the question, well, what came before? Very seductive question, ladies and gentlemen. It was only when people started to think about the implications of Einstein's own theory that they realized that the universe had to have come and sort of exploded out from a point in some way, shape or form. We'll cover that in a later video, by the way. But there must have been something like that where the universe must have actually started a finite, specific time ago, which was very worrying for people. So this is a process that happened throughout science. There has been people saying sort of like, oh, here's some evidence. Maybe these things are chunky or finite. And then there's people take the pipe out of their mouth. Nonsense! You're talking poppycock! We all know that things are smooth, and that process is still going on today, ladies and gentlemen. So that process of assumption of symmetry at scale is a very, very powerful force. And not only does it make it easier for the human mind to think about, but it also makes it easier to reason about mathematically. And that is one key reason why infinity has this persistent appeal. So the best tool by far, ladies and gentlemen, that we have for understanding, for instance, electric fields or a huge number of different phenomena that show up in physics is calculus, and all of the incredible sort of magic tower of tools that we've built on top of calculus. Because calculus only gives you perfect answers when you are looking at systems which are completely smooth. The idea of calculus is that, but here's the thing about it. Calculus is this rule that says, don't sweat the small stuff. And that's how it was conceived originally, ladies and gentlemen, by Newton and Leibniz. Essentially what you do is you sort of say, like for instance, I'm pouring water out of a jug, as I was doing earlier. We say, I'm pouring this amount out, and we can sort of say, oh, let's look at the moment in which he poured that out, how much water fell out of the jug. And then we can look at a smaller moment and say, oh, look, here's an even smaller moment where he poured even less. And then you get right down to looking at essentially what is the rate at which water is coming out of the jug. And when you try to sort of divide it down into infinitesimal amounts of jugginess, that's the point at which you start dealing with notional infinities, and then you brush them swiftly under the rug and say, don't worry about that. And when you do that, you still get the right answer. And you know what? You can use that effect to calculate the water that's pouring out of a jug just fine. Nobody expects to find fractional water molecules, though. Biologists use calculus to model populations. No one expects to walk into a field and find pie bunnies hopping about. Nobody expects, economists use it. Nobody expects you to go into a shop and see sort of, a basket of fruit that costs e to the 10th. Not a thing. Continuous values don't show up in these other domains, and yet we can still use calculus just fine. So why do physicists love it? Because physicists are the people who are stuck with the incredibly hard job of trying to look for the ultimate rules, the ultimate pattern by which the entire universe works. So that's a pretty good reason for them to try to want to look for something that's perfectly smooth. But there are other models that I would propose work, in fact, somewhat better, in which what we do is we divide space up into tiny nuggets. I mentioned one in my black hole video, where we essentially we decide there are atoms of space and then model around the idea of atoms of space. And this turns out to be a tremendously interesting and effective approach that solves a great deal of the problems that have been bedeviling the fight between relativity and quantum mechanics for the last century and change. So there are good reasons to believe that once you get down to what's called the Planck length, ladies and gents, the smoothness just simply goes away as an idea. And there's plenty of reasons to believe that we can do that. Because if you try to model, for instance, a single atom, a hydrogen atom, I believe this is the correct analogy, but model a hydrogen atom in terms of these units of Planck length spacetime, the tiny distance at which all distance seems to lose meaning, what you might think of as the size of a spatial nugget. Well, if you basically have a grain of each, if you make each one of those tiny spatial nuggets the size of a grain of sand, a hydrogen atom is about the size of the entire Milky Way. Not just all the beaches in the world, ladies and gentlemen, the entire Milky Way. So that gives you plenty of orders of magnitude for things to look smooth in. You don't need to invoke infinite smoothness. There's no point. You've got loads of room to play with. And the same thing happens when you model up to very large scales. One reason why people talk about an infinite universe is because when we look at the universe, it appears to be what's called topologically flat. We sort of think if the universe was sort of bent in on itself, if it was some kind of closed surface, and we'll cover this in another video, then then what you would find is that you would find evidence of that curvature. When we look towards the Big Bang, we look out into space, there'd be some kind of evidence that the universe was sort of curved, as scientists say, on large scales. We don't see that. And so people say, well, there's evidence at least that it seems to be an infinite universe. To which I would say, nonsense! There is no way in which you can actually have evidence that something is infinite. By definition, it's not an evidency kind of a thing, because no matter what scale you look at it at, there might be some scale just beyond it in which it happens to just be large, or in terms of smoothness, just happens to be made of little bits. You can't test for infinity, it's not testable. And that's the fundamental reason why infinity is nonsense. So when you look out to the universe at large scales, yeah, I suppose in some random trippy psycho universe it might be infinite, or on the other hand, it might just be big. I think that they managed to test that the universe may need to be about 1,000 times the size of what we can test or examine, and we look at the universe and like a full 1,000 times, ladies and gents. That is not enough evidence that the universe is infinite. Because what happens if the universe, for instance, turns out to be 10 to the 50 trillion times larger than what we can see? Have we got enough data on hand to prove that that's not the case? And the answer is a giant flaming no. A giant flaming no. And yet, 10 to the 50 trillion is an indifferently small size compared to the size of an infinite universe. So it seems a little unwieldy, shall we say, to presume the universe is infinite based on the information that we currently have access to. Now, there are some physical theories that do a handy job of imagining what's going on with you, make use of things called inflaton fields and the like, that sort of mostly work the way that people have them panned out if they suppose an infinite universe. But what I would propose is that if you've got infinities baked into the description of your universe from the get-go, chances are you're on shaky ground. And we'll cover more of that. We'll talk about that in other videos as well, again, of course. But I've probably covered enough, ladies. Jet infinity, not really a thing. If somebody tells you the universe is infinite, don't buy it. If somebody tells you that you get down to the fundamental level of the universe and everything is made of a flux of sort of n-dimensional magical weirdnesses and their extra secret hidden dimensions, don't buy that either, ladies and gents. They don't know. They actually don't have the data to back it up. And furthermore, it's unscientific. Thank you for watching and listening. Tune in next time for more.